In the previous lecture, we were discussing about the Carnot heat engine and Carnot refrigeration cycle. And we have studied the concept of reversible and irreversible processes. And we now know that the best possible process, or which is free of any losses, is the reversible, fully reversible process. A fully reversible process is one in which both the system and the surroundings will return to their original condition or the original position when the process is reversed. And then we discussed the cycle, the heat engine cycle and the refrigeration cycle, in which we can at least assume theoretically that all the processes are fully reversible. So it means such an ideal cycle or engine or a refrigeration cycle in which we assume all the processes are fully reversible, then that type of engine or cycle is known as Carnot heat engine or Carnot refrigeration cycle. Right, so now we should be very clear about the concept of a fully reversible engine or a refrigerator and actual engine and refrigerator. Actual heat engine or actual refrigeration cycles will have losses in every single process of this cycle, of these cycles, right? But to have an ideal heat engine cycle, or to have the concept of an ideal refrigeration cycle with which we can compare any actual engine or any actual refrigeration cycle. So the purpose of having this concept of Carnot heat engine or Carnot refrigeration cycle is that we want to have a benchmark or the cycle which can give us the maximum possible efficiency, whether it's a heat engine or a refrigeration cycle. Because we know the maximum possible efficiency of an ideal heat engine is also less than 100%. We have already discussed. Then we are interested to know what is the maximum possible. So that's why we have this imaginary or theoretical ideal heat engine and theoretical ideal Carnot refrigeration cycle. The concept of this Carnot heat engine or a Carnot refrigeration cycle. So now, based on this concept, we have this next concept, which is known as the Carnot principles. Here we can explain these principles, the Carnot principles, with the help of that figure. So what this figure shows, for example, there are three different heat engines. This first one is an irreversible heat engine, means the actual or practical heat engine. These two are fully reversible heat engines. These two engines, maybe it is a reciprocating type engine, that is some rotary type of engine, but both are fully reversible heat engines. So what are the Carnot principles? And all these heat engines, for example, are operating between these two temperatures. This is high temperature or high temperature reservoir and the low temperature reservoir temperature or sink temperature TL. So all these heat engines are operating between this high temperature source and this low temperature sink. Now, what are the Carnot principle? Carnot principle simply says that the efficiency of an irreversible heat engine will always be less than the efficiency of a reversible heat engines operating between the same two temperatures, between the same TH and TL. The efficiency of an irreversible heat engine will always be less than the corresponding reversible heat engine between the same TH and TL. Similarly, the second principle is that the efficiency of any reversible heat engine, of any type of reversible heat engine. For example, this engine is for example a steam power plant. This engine is, for example, a reciprocating automobile engine. But if both are fully reversible And if both are operating between the same TH and TL, then their efficiency will always be equal. That is the second Carnot principle, that any type of reversible heat engine. So now it means if we say that this is the principle, that the efficiency of any type of reversible heat engine will always be same under fixed TH and TL, then it means the efficiency of such engines are independent of the type of reversible heat engine, and also their efficiency are independent of the working fluid which is used in these engines, right? So the reversible heat engines of any type of having any type of working substance which is used to operate these cycles, their efficiency will always be same. So now it means the efficiency of a reversible heat engine is only dependent upon the temperatures, the maximum or the high temperature source and the low temperature sinks. Their temperatures will define their efficiency. And so the fully reversible heat engine efficiency will always be greater than the corresponding irreversible heat engine operating between the same TH and TL. So these are the two Carnot principles which I have explained, and these are written here, right? So and these two statements, or these two Carnot principles, can be proved by demonstrating that the violation of one will also make the second proposition wrong. So for example, if we say that this principle is not correct, so then this will make this principle also incorrect. It is the same thing which we have a similar concept which we have already discussed in the case of Kelvin-Planck statement versus Clausius statement. There we said that if the Kelvin-Planck statement is assumed to be wrong, then it will also make the Clausius statement also wrong. So the similar concept is applicable here, and this can be proved, so which you can study by yourself. So on page 297 to 298 from the Sangel's 8th edition book. So but you just need to actually remember these two principles, that the efficiency of any heat engine will always be less than, or maximum it would be equal to, the efficiency of a reversible heat engine. And the efficiency of any reversible heat engine operating between the same two reservoirs will always be same. Okay, so the next is the thermodynamic temperature scale. Now we have said that the efficiency of any reversible heat engine or a fully reversible refrigerator, their efficiency is only dependent upon the temperatures, temperature TH and temperature TL. It is not dependent upon the type of engine or the type of a refrigerator, right? So that's why the efficiency of such engines or refrigerators, they are only a function of temperatures. Now what is the temperature scale, which is also independent of the properties of substances? We know that the temperature scale, which is independent of the properties of the substances, is known as the thermodynamic temperature scale, and thermodynamic temperature scale is the absolute temperature scale, which is Kelvin in SI units or Rankine in the British units. So efficiency of a reversible heat engine is independent of the type of working substance which is used, and the properties of that working substance, how the cycle is executed, or what is the type of reversible heat engine. So it is independent of all these things. It is only dependent, the efficiency of a reversible heat engine or a refrigerator is only dependent upon the temperatures, the high temperature source, the temperature of this high temperature source, and the temperature of this low temperature sink. And what are those temperatures? Those temperatures are actually the thermodynamic temperature scale, and those thermodynamic temperature scales are absolute temperature scale. So efficiency, theoretical efficiency of any reversible heat engine is only a function of TH and TL, right? Or in other words, we can also say that QH by QL, the heat which is supplied from a high temperature source and heat which is rejected to the low temperature sink. Or it could be a heat which is absorbed from the low temperature sink if it is a refrigerator, and QH will be the heat which is rejected to the high temperature source if it is a refrigerator. Right, so this QH by QL, this ratio QL by QH or QH by QL is also only is equal to a function of TH and TL. In other words, QH by QL for a fully reversible heat engine is equal to TH by TL. That is true only for a fully reversible heat engine, not for an irreversible or any actual or practical heat engine. That is not true. This is only true for a fully reversible heat engine. And we can prove this fact that this QH by QL ratio is equal to TH by TL ratio. This can be proved mathematically also, and we shall prove this thing in chapter 8 when we will have the concept of entropy. And the concept of entropy is based on the concept of reversible and irreversible, which we have already discussed. So we shall prove this fact with the help of a simple mathematical derivation in chapter 8 once we shall cover the topic of entropy. So what this says that the ratio of QH by QL is equal to the ratio of TH by TL for a fully reversible heat engine, because the efficiency of a fully reversible heat engine is only a function of TH and TL. So that's why this is also true, right? This ratio is same. It doesn't mean that QH is equal to TH, or it doesn't mean QL is equal to TL. It is only about the ratio QH by QL, QH which is supplied at this temperature, and QL the heat which is rejected at this temperature, the low temperature sinks. The ratio are same. So we shall prove it in chapter 8. Right, so the thermal efficiency of a Carnot cycle and the absolute temperature. So what is the relation between the thermal efficiency of a Carnot cycle and the absolute temperatures of these two reservoirs? And what are absolute temperatures in Kelvin or Rankine, TH and TL? We already know the general definition of efficiency. Thermal efficiency of any heat engine is equal to 1 minus QL by QH. We have already discussed how the efficiency can be written in terms of QL by QH, because we know efficiency is actually equal to W dot divided by Qin or QH. And this W can be written as QH minus QL divided by QL. So this is the equation which is written here. And for a Carnot cycle, only for a Carnot cycle, it means only for a reversible heat engine, we can replace this ratio with this one, right? So we can replace this ratio with this ratio only for a Carnot cycle and not for an actual or irreversible cycle. That is true only for Carnot cycle. So I'm repeating again and again because this is something which should be very clear to all of you, that only this ratio can be written in terms of temperature ratios for a Carnot cycle or a reversible cycle. The derivation of this thing, this term, that QL, this ratio QL by QH is equal to TL by TH, is also available in this book of Sonntag, 8th edition, right? in section 5.8 in chapter 5, Fundamentals of Thermodynamics by Bortnak, where they have proved this fact for a Carnot cycle. Right, so you may study from there. It is not included. This proof is from this book is not included in your curriculum, but only if you are interested to know how this is true, or how it is derived, or how it is mathematically proven. So you can go to this book. Otherwise, we shall be proving it. We shall derive this equation in chapter 8, right? Okay, ji. So now what is the conclusion? Whatever we have discussed so far in this chapter, the overall conclusion is that the efficiency of any heat engine is given by 1 minus QL by QH, or it is equal to W by QH. That is the general definition of efficiency, which is applicable to any heat engine. Any means here, it could be a reversible heat engine or it could be an irreversible heat engine. So that equation, that general equation of efficiency, is applicable to both reversible or irreversible heat engines. But this particular form of efficiency is only applicable for a Carnot heat engine, or in other words, the fully reversible heat engine. So that is the general definition of efficiency. 1 minus QL over QH is equal to W over QH. It is true for any reversible or irreversible heat engine. But this particular definition of efficiency, where we have replaced QL by QH with this ratio TL by TH, is only applicable to Carnot heat engine or fully irreversible heat engine. Right. So this equation actually gives us the highest possible efficiency of any heat engine which is operating between these two temperatures, TL and TH. So for a given TL and TH, for example, TL is in Kelvin. Of course, it's a single T, so it will be in Kelvin. For example, sink temperature is 298 Kelvin, and the source temperature is, for example, is 500 Kelvin. Right. So then 1 minus this TL by TH, that is the maximum possible efficiency which we can get from any heat engine, because that is the maximum possible for a reversible heat engine, and the efficiency of all other heat engines which are irreversible will always be less than the efficiency of this reversible heat engine when these heat engines are operating between these two temperatures. So for these two temperatures of TH and TL, this correlation 1 minus TL by TH will give us the maximum possible efficiency, right? So that is the use of this Carnot heat engine or Carnot refrigerator concept, that it gives us the maximum possible efficiency, or it gives us an idea about the maximum possible efficiency which can be obtained from any heat engine. So any other heat engine will have efficiency less than this value for this TH and TL. That is the use of Carnot heat engine concept, or the Carnot heat engine efficiency. Right. So both TL and TH are the absolute temperatures. If we use Celsius or Fahrenheit, it will give us the wrong results. It will give us wrong results. So these temperatures are always absolute temperatures. Next, so this slide summarized what we have discussed in the previous slide. That, for example, there is heat temperature source or high temperature reservoir or high temperature source available at this temperature, and there is a low temperature reservoir or the sink available at this temperature. Now for example, this is a fully reversible heat engine. Now we can find out its efficiency from this simple equation, 1 minus TL over TH for a fully reversible heat engine. So by putting these values, 300 divided by 1000, the maximum possible efficiency between these two temperatures is 70%, given by a fully reversible heat engine or a Carnot heat engine. So for example, this is another heat engine which is irreversible heat engine, and its efficiency is lower than 70%, then that is definitely possible. But if there is such a heat engine, if someone claims that he has a heat engine which can give efficiency of 80% when it is operating between this TH and this TL, and but then this is impossible because this efficiency is higher than the corresponding Carnot heat engine efficiency. So such an heat engine is impossible, right? That is not possible, right? So that is the purpose of showing this diagram, that the efficiency, no heat engine, it is written here, no heat engine can have a higher efficiency than a reversible heat engine operating between the same high and low temperature reservoirs. So that is explained here, or that is written here. The performance of all the actual heat engines, which are irreversible heat engines, right, should not be compared. The efficiency of all the actual heat engines should not be compared with 100%. Right? It should be compared with the efficiency of a reversible heat engine, right? This one. So the efficiency of actual heat engines should be compared with this one, because this is the maximum possible. Maximum possible is not 100%. Maximum possible is the one which is given by this equation of Carnot or fully reversible heat engine. So because that is the true theoretical limit, right, between this TH and TL, and not the 100%, right? Even Carnot heat engine cannot have an efficiency of 100%. Okay, so now let's solve a numerical. An inventor claims to have developed a power cycle capable of delivering a net work output of 300 kilojoules for an energy input by heat transfer of 700 kilojoules. So an inventor has claimed that he has developed some power cycle, means a heat engine, which is capable of delivering a net work output. So it is capable of delivering a net work output of W dot of 300 kilojoules for an energy input when the energy input is 700 kilojoules in the form of heat, right? So it means that is QH. The system undergoes the cycle the system undergoing the cycle receives the heat transfer from hot gases. So this heat engine, which is undergoing a cycle, it is receiving heat from this high temperature source, which is at 500 Kelvin, and discharges energy by heat transfer to the atmosphere at 290 Kelvin. So that is the claim of that inventor, that he has developed that heat engine which is consuming this much heat and producing this much power or work output, and that is when this heat engine is operating between this TH and between this TL. So now we need to check that whether his claim is true or not. So how we can check? We can simply compare the efficiency of this heat engine, which has been developed by that inventor, right, with the efficiency of a corresponding Carnot heat engine operating between same 500 and 290 Kelvin. So the efficiency, the maximum possible efficiency of a heat engine operating between 500 Kelvin and 290 Kelvin is given by this one. That is the maximum possible, right? 1 minus dn over dh. So simply put in the values, 1 minus dn over dh, that comes out to be 42%. So the maximum possible efficiency of this heat engine, if it is fully reversible heat engine, is this one, right? So you can see it is far less than 100% because the temperature TH is not so high, TCDL is not too low, right? So now what is the efficiency of this heat engine? Because that is an irreversible, because that heat engine has been developed by an inventor, so it means that this heat engine is an irreversible heat engine, and the efficiency of an irreversible heat engine is not this one, it is this equation, the general equation. So here we can put W net over QH. W net is given 300 kilojoules, QH is given 700 kilojoules, and that comes out to be 42.9. Now if we compare this efficiency with this efficiency, so you can see that the efficiency of this irreversible heat engine is more than this one. So it means, so what is it saying? That the efficiency of this thermal efficiency of this irreversible heat engine developed by that inventor, this efficiency is greater than the maximum possible thermal efficiency if the same heat engine is fully reversible. So that his claim is not correct. His claim is wrong because he has developed such an heat engine whose efficiency seems to be more than the corresponding efficiency of a fully reversible heat engine. So his claim is not correct. So it means this is a perpetual motion machine of second kind, right? Because it violates the second law of thermodynamics, right? Because this much of heat cannot be converted into this much of work. Because if this heat is converted into this work, then the efficiency comes out to be more than the efficiency of a Carnot heat engine. So his claim is not correct. So that's how we can check the claim of any inventor who develops any new engine, and if he claims that the efficiency is this much, so then we can compare the efficiency of any inventor with the efficiency of a Carnot heat engine. So the efficiency of any inventor should be less than the efficiency calculated on the basis of Carnot heat engine efficiency. Let's do another problem. A heat engine is operating on a Carnot cycle and has a thermal efficiency of 55%. Right. So for example, this Carnot cycle has an efficiency of 55%. Right. The waste heat from this engine, is rejected to nearby lake at 60 degrees Fahrenheit. Right, so that is the heat which is rejected to a nearby lake at a rate of, and at what rate? 800 BTUs per minute. So this heat engine is rejecting heat to this lake at 60 degrees Fahrenheit, and how much heat is rejected? 800 BTUs per minute. And this is a Carnot cycle. So that is given here, that heat engine is actually a Carnot heat engine. Determine the power output of the engine. So we need to determine the power output of the engine and the temperature of the source. Temperature of the source means this TH is to be calculated. TL is given, that is in 60 degrees Fahrenheit, so we need to convert it into Rankine, right? 460.67 plus 60, 520.67 Rankine. That is the absolute temperature of this low temperature sink. Now QL is given. So part A is to find out the power output. So power output means W dot net we need to calculate. So which can be calculated from the efficiency equation. What is efficiency? Efficiency is equal to W dot over QH. But here QH is not given, so we cannot use this equation. W is unknown, QH is unknown, so we cannot use this equation. So that's why we go to the second equation. We can write the same equation in this form also. So here 50 efficiency is given, 1 minus QL over QH. So from here, first of all we can calculate the QH, Q dot H, which comes out to be 1,777.8 BTUs per minute. Now we can put here in this equation to find out the work output, because efficiency of that heat engine is given, right? So from here we can find out the net work output from this heat engine, and that is 977.8 BTUs per minute. So that was part A. Second part is to find out the temperature of the source, means this pH we need to calculate. So for that, we also know for a Carnot heat engine, only for a Carnot heat engine, that ratio QH by QL is equal to TH by TL. So from here we can find out TH, because QH is calculated here, QL is already given, TL is given. So from here we can find out TH. So TH will come in absolute temperature scale 1155.6 Rankine. So that is one thing which you should always be careful, that these temperatures are absolute temperatures. So that's why this Fahrenheit must be changed to Rankine. So the next or the last topic of this chapter is the quality of energy. Let's explain this concept with the help of that example. For example, there is a reversible heat engine operating between this TH and TL. So for example, TL is fixed 303 Kelvin, which is the normal atmospheric temperature, or the normal naturally available sinks are normally at this temperature, 303 Kelvin, right? So about 30 degrees Celsius. So if TL is fixed, because this is the temperature of the naturally available sinks. Now we can see the effect of TH on efficiency of this reversible heat engine. And what is efficiency of a fully reversible heat engine is 1 minus TL over TH, right? So with the help of this equation, we can find out the effect of TH. This equation simply says that the efficiency will increase with increase in TH, or in other words with decrease in TL, right? So if we keep on decreasing this TL, then efficiency will increase, but we cannot decrease this TL because naturally available sinks are normally at this temperature, right? So for example, if this TL is 0 Kelvin, that is the minimum which we can achieve, only then this efficiency will be equal to 1 or 100%. So that is the only possibility. To have 100% efficiency is to have TL at 0 Kelvin, TL equal to 0 Kelvin, which is of course not possible. So what is the other possibility then to increase this efficiency is to increase this TH, because here TL cannot be reduced below these values, right? So then what is the other factor which is affecting the efficiency of heat engine, and that is the temperature of source, or the temperature at which this QH is supplied, right? So here you can see the effect of TH on efficiency, Carnot heat engine efficiency, by keeping TL fixed. So for example, in this equation, this key TL is fixed 303 Kelvin divided by TH. So first assume value of 925 Kelvin, then efficiency. So here it will be 925. So 1 minus 303 divided by 925 is equal to 67.2. So if you keep on decreasing this TH, the efficiency is continuously dropping. So at 350 Kelvin, the efficiency is only 13.4. And what is this efficiency? That is the maximum possible efficiency of this reversible heat engine. as a function of TH. So here you can see even if it is a fully reversible heat engine, but because TH is so low, 350 Kelvin, and TL is fixed, then the efficiency of this fully reversible heat engine is only 13.4. So the efficiency of actual heat engines will be even less than 13.4. So what this table shows us that the efficiency is the function of temperature, high source temperature. So it means the efficiency is dependent upon the temperature. It is not QH, it is actually TH at which this QH is supplied. So that is energy, but that is not energy. Temperature is not energy. So we can say that temperature is actually representing the quality of energy. You can have a huge amount of QH available at 350 Kelvin, but the efficiency will be only 13.4. We can have a huge amount of QH, but at a very low temperature of only, for example, 350 Kelvin, right? Therefore, the maximum efficiency which we can obtain, even if this QH approaches to infinity, the only 13.4% of this QH can be converted into useful work here at this point. So if you have the same infinite, a huge value of QH at higher temperature, for example, 925 Kelvin, then 67% of this huge QH can be converted into W, 67%. So it means the efficiency is not just about the quantity of energy, it is actually the quality of energy. And quality is described by this temperature, the temperature of this high temperature reservoir or the heating source. Otherwise, so that is the concept, what is meant by quality of energy. Quality of energy is actually described by the temperature of the high temperature reservoir, right? The source temperature represents the quality of energy, right? So second law of thermodynamics is telling us that efficiency is a function of temperature. And what is temperature? Temperature is actually quality, represents the quality, right? So how the quality of energy increases with the rise in temperature. So as the temperature rises, the quality of this thermal energy increases. Here you can see an example. For example, the solar ponds, or what solar pond is a concept to store a large amount of energy of the sun in water. So you can make a huge amount of big ponds to capture the freely available energy of the sun using this device, which is known as solar pond. So what is solar pond? In solar pond we create 3 different layers. Here layers of water. Here it is very salty water. The lowest layer is very salty water. The intermediate layer is less salty, means the amount of salt which is mixed in that water is its concentration is lower than this one, and the top surface is simple fresh water. So that's how we can create 3 different layers of waters, because here we have a very dense water because a large amount of salt is mixed. Then we put a layer of less dense salt, and less dense water means less salt is mixed in this water, and at the top we have a fresh water. So we can create such reservoirs of water, of huge reservoirs of water. And now what it can do, it can absorb the solar radiation, because this fresh water will allow the maximum radiation to pass through. Some of the radiation will be absorbed here in the salty water, but the maximum radiation, because this very salty water has the ability to absorb maximum of this solar radiation. So whatever radiation which reaches here, it is absorbed by this body of water, which is a highly dense water, highly dense salty water. These two layers will only allow these radiation to pass through, and these are acting as insulation to capture or to keep this heat here, and so that this heat is not transferred back to ambient, because ambient temperature is low. This ambient air is not absorbing the solar radiation. So the radiation passes through this ambient air. Because it is not absorbing, that's why the temperature does not increase. So this solar energy is actually absorbed by this very salty water. So here temperature can be increased, but this temperature which we can obtain by building such ponds is maximum in the range of 350 Kelvin. Right, 350 Kelvin. So although it's a huge amount of energy, because here we can have, for example, very huge amount of mass into Cp product, huge thermal capacitance of this water available, but the maximum temperature which we can get using such device is only 350 Kelvin. So now let's read what is written. Large quantities of solar energy, for example, can be stored in large bodies of water called solar ponds but only at about 350 Kelvin. So efficiency of solar ponds is very low, under 5%, because maximum possible is 13%. So the actual efficiency of solar pump, because we can use this hot water to run a steam turbine, because this will act as a boiling source. And after boiling you have a turbine is, after turbine there is a condenser pump, so we can have a steam power plant which is taking the heat of this pond. But because the temperature of this pond is only 350 Kelvin, that's why the maximum efficiency is only 13.4. So to increase the efficiency, we have to increase the quality. So then we have to use another different type of solar collector or solar system that is known as concentrator. Here the solar radiations are actually concentrated when those are actually striking this reflecting surface, which is known as concentrator. Now it concentrates all the solar radiation onto a single point. So using such a mechanism, such a device of a solar based system, here the temperature can be achieved to maybe, for example, up to 600 Kelvin. Right. So here you are not concerning about the amount of energy, we are concerning about the quality of energy. So using such device we can have a low amount of water but at a very high temperature. Here we have a huge amount of water but at a very low temperature. So this is a very low quality energy, and here we can obtain a very high quality of energy. So quality is described by the temperature. Quantity is the same, Q. Q is representing W, Q's, W's, these are actually the quantities of energies. But we are here concerned about the quality of energy. Right, so the last sentence, let's discuss this one. So I hope the concept of quantity and quality of energy is now clear. So when heat is transferred from a high temperature body to a low temperature one, it is degraded. Because when heat is supplied from a high temperature body to a low temperature body, now it is degraded, because now when the temperature of this source drops, then less of it is available to be converted into work. When the temperature is high, then maximum of it can be converted into work. So during any process, during any heat engine process, what is happening, the high temperature body is now converted to a low temperature body, because by losing this heat, the temperature of this source will drop. So as the temperature is dropping, we can say that the energy is degraded, because with the drop in temperature, its ability to convert into work is also dropping, because the efficiency drops. So whenever heat is transferred from a high temperature body to a low temperature one, it is degraded. Degraded means the quality of energy is degraded. Quantity does not degrades. Quantity just transfers from one place to another place. So the body whose temperature is dropped during any heat transfer process, now we can say that the energy is degraded. Okay. So now let's solve one more problem. A Carnot heat engine receives heat from a reservoir at 900 degrees Celsius. So let me draw its diagram. So there is a Carnot heat engine. Carnot heat engine. So that should be clear that we are talking about a fully reversible heat engine. It receives heat from a reservoir. So it receives heat from a reservoir which is at a temperature of 900 degrees Celsius. So TH is equal to 900 degree Celsius. Right. At what rate? So this QH is also given 800 kilojoules per minute. That is 800 kilojoules per minute. And rejects the waste heat. Now this heat engine, what it will be doing, it is converting this QH into W, right? And then rejecting certain amount of energy to some low temperature reservoir. For example, here we have a reservoir at 27 degrees Celsius. And what is that reservoir? That ambient air at 27 degrees Celsius. So it means that 27 is actually TL for this heat engine, right? So a Carnot heat engine receives heat from a reservoir at 900 degrees Celsius at a rate of 800 kilojoules per minute and rejects the waste heat to the ambient at 27 degrees Celsius. The entire work output of this heat engine, is used to derive a refrigerator. So it means this work is used to derive a refrigerator, because we know to operate a refrigerator we need work input in the compressor. So what this refrigerator is doing, this refrigerator removes heat from a refrigerated space at -5 degrees Celsius. So what this refrigerator is doing, it is removing heat from a space at -5 degrees Celsius. So this is actually TL for refrigerator, and it is removing heat QL. For a refrigerator, this heat removed is QL. For a heat engine, this heat which is absorbed is QH from this high temperature source. But refrigerator is absorbing heat from a low temperature source, from a low temperature TL temperature source. And what is it doing? And transfer it to the same ambient. Now it is transferring this, because every refrigerator has a condenser where it loses heat. So here it is losing heat, but that is at a higher temperature. For a refrigerator, it is rejecting heat to a high temperature. For a refrigerator, it is a high temperature because it is absorbing heat from -5 degrees Celsius and rejecting it to a high temperature, which is 27 degrees Celsius. But in case of heat engine, this 27 is a low temperature source because it is absorbing heat from a high temperature source of 900 degrees Celsius and rejecting it to a low temperature. So that should be very much clear. Here QH is QL for refrigerator. Here QL of a heat engine is actually a QH for a refrigerator. So that is the system. We have a heat engine is there, a Carnot heat engine is deriving a Carnot refrigerator. So it's a Carnot heat engine and also a Carnot refrigerator, which we are talking about. So determine the maximum rate of heat removal from the refrigerated space. So it means what is the maximum rate of heat removal. So this is the refrigerated space from which heat is removed. Here is the heat which is removed, and we need to calculate this one. And what is, how much, which heat to be calculated, maximum possible. What is given? What we have to calculate is this one, QLR maximum. So when a refrigerator will absorb maximum heat, when this refrigerator is operating as a fully reversible refrigerator, means this refrigerator is a Carnot refrigerator. Because here in this problem it is given that this is a Carnot heat engine, but it was not clearly written that the refrigerator is also a Carnot refrigerator. But from this part A, the statement of part A tells us that we have to assume this refrigerator a Carnot refrigerator, because here we want to find out the maximum rate of heat removal from the refrigerator space. So refrigerator, the purpose of a refrigerator is to absorb heat from a refrigerated space, and when it will absorb maximum of it only when it is operating as a Carnot refrigerator. So that is part A, to find out this QL maximum. Part B is the total rate of heat rejection to the ambient air, the total rate of it. So let's first solve part A. So this figure which I have drawn is already drawn here. So I drew it again just to explain it. So actually it is drawn here separately. Okay, so we need to find out QL. How we can find out QL of this refrigerator? We know the efficiency of a refrigerator, which is known as the coefficient of performance. Coefficient of performance of a refrigerator is given by Q dot L, useful output or desired output, divided by required input, which is W. And from this equation we can find out QL, but here W dot is unknown, and also COP of a refrigerator is also unknown. So this equation has two unknowns. So we need some other equation to calculate COP. So we know the efficiency of a reversible refrigerator can be written in terms of TH over TL, because we know the refrigerator efficiency, COP of a refrigerator, can be written as QL divided by QH minus QL, right? So that QH minus QL can be written in terms of TH by TL for a Carnot refrigerator, right? So now just by putting values of this TH and TL for a refrigerator, TH is this one and TL is this one. That is a COP of a reversible refrigerator. That form of efficiency is for a reversible or irreversible refrigerator. This particular form, just like for a heat engine cycle, is only for a reversible heat engine. Right. So just by putting values, TH and TL both should be Kelvin, absolute temperature scales. So that is the COP of this reversible refrigerator, and it is 8.37. We have already discussed that COP can be greater than 1. Right. So now we know COP. Now we should also know what is W dot. Right. That W dot coming from heat engine. So to calculate this W dot, we have to solve this function to find out this W dot. Only then we can put it here, and to find out this Q dot L, maximum Q dot L. So how W dot can be calculated? So let's see here in the heat engine part. So the efficiency of this heat engine That is the efficiency of a refrigerator, Carnot refrigerator, and that is the efficiency of a Carnot heat engine. So that is given by 1 minus dl over dh. So just by putting values, we can find out the efficiency, and that comes out to be, so from here, that is 0.744 or 75.4%. So now we can calculate the efficiency of a heat engine, because efficiency of a heat engine is also equal to W divided by QH. So put that efficiency in this equation to find out W. W dot is equal to efficiency into QH. So just by putting values, so that comes out to be 595.2 kilojoules per minute. Right. So that is W dot of heat engine, and this W dot is actually used here to derive the refrigerator. So this W dot is, we can put it here to find out Q dot L, because COP of this Carnot refrigerator is calculated from the other equation. Right. So from 1, Q dot LR is equal to 595 multiplied by 8.37. So that is the unknown, the maximum rate of heat removal from the refrigerated space, that is 4982 kilojoules per minute. So be careful about the units, it's throughout kilojoules per minute, so the same units are being used here. Okay, so the second part is to find out the total rate of heat rejection to the ambient air, because both heat engine and refrigerator both are rejecting heat to the same ambient. So the total heat which is rejected to the same ambient is QLHE from a heat engine plus QH of R of a refrigerator. That is the total amount of heat which is being rejected to the same ambient at 27 degrees Celsius. So the heat rejected, total heat rejected. So the heat rejected by the heat engine is given by, so if we say only heat engine, if this is our system, then this QH minus W is equal to QL. So QH, Q dot of heat engine minus W net out of a heat engine represents the Q dot L, or the heat rejected by a heat engine. Right. So 800 minus 595, because we already know what is the QH of heat engine, and W dot net out we have already calculated W dot net. So that is the heat energy which is rejected by the heat engine part. Similarly, for the refrigerator part, what is QHR? If this is our system, then this QL plus W, these are the energy in, is equal to energy out, which is QHR. So QHR is equal to Q dot LR, Q dot L, heat which is absorbed from a low temperature source by a refrigerator, plus W dot net out. Right, so that is 557.2 kilojoules per minute. So the total heat which is rejected to the ambient is QL HE plus QHR. So just sum these two. So that is the total energy which is rejected, right, to the same ambient.